Hello dear students, welcome to the Artificial Intelligence and Machine Learning Lecture 5. Today we are going to see Perceptron Learning, which is one of the most important algorithms of machine learning. It is also the core of neural networks. Probably you have already heard them previously. So I am hoping that you will give extra attention to this lecture, the Perceptron Learning. Okay. So let's start.
Machine learning models. Some machine learning approaches make strong assumptions about the data. If the assumptions are true, this can often lead to better performance. If the assumptions aren't true, they can fail miserably. Other approaches don't make many assumptions about the data. This can allow us to learn from more varied data. But they are more prone to overfitting, and generally require more training data.
Okay, so there are two type of approaches. One that makes strong assumptions about the data, and the other one doesn't make strong assumptions about the data. What does this mean? What can this mean? Let's say you are going to separate apples and bananas. You can make a strong assumption that all bananas will be round. I mean banana shape is called as, it will be curved. Probably it was the curve, yes, and apples will be round. So these are strong assumptions about our data model. However, let's say you are going to let's think a good example about that. We can't make strong assumptions for a data. Let's say you are going to separate clouds from other objects, and you know that clouds can have very different type of shapes. Therefore, you can't make a strong assumption about clouds. And for classifying clouds, you would need an algorithm that would not make strong assumptions about the data. Okay, so depending on your data, you have to pick your algorithm carefully. If your data cannot be generalized and your algorithm is making strong assumptions, then your algorithm may miserably fail. So,
What is the data generating distribution?
so you see that we are generating a data set for our training. Okay. So the data generation and data distribution is important part of the machine learning, especially in training. How you are going to distribute your data, or let's say generate your data, may affect your final results, final output. So what we are meaning here is that what would be our assumption about the data? Okay, so if we are knowing that blue class is blue class have a circled model, then we can make an assumption about this data and easily classify blues and reds separately. If we are knowing that they will be like this in the final form. So how data is distributed and how much about it we know affects our algorithm performance and our results. Okay.
Model assumptions. If you don't have strong assumptions about the model, it can take you longer to learn. Assume now that our model of the blue class is two circles.
So when we have assumption about our model previously, then it is much easier to classify our model. Okay, because we know that they will have two circles. The blue class will have two circles. So this is what it means. Okay, let's try to understand from here.
Knowing the model beforehand can drastically improve the learning and the number of examples required.
Since we know that they will have two circles, we can start defining the boundaries of the circles with just single data. It can be either like this, follow my mouse cursor, or it can be either like this, because it will be a circle, and we know that. Therefore, we can drastically improve our algorithm performance, training performance, and accuracy with that beforehand knowledge. However, if we assume that there will be two blue circles, however, if there is actually there are two red circles, then our algorithm would perform miserably bad. Why? Because we assumed that the blue data will have circles. However, in actually the red data has circles. So it is important to have correct assumptions or knowledge about our dataset. Okay.
Machine learning models. What were the model assumptions, if any, that KNN and decision trees make about the data?
Okay, so what were the model assumptions that KNN or decision tree is making? If you try to remember,
KNN is a non-parametric lazy learning algorithm. That is a pretty concise statement. When you say a technique is non-parametric, it means that it does not make any assumptions on the underlying data distribution.
so KNN doesn't make any assumptions about the data. Okay. So what is also lazy learning mean?
In machine learning, lazy learning is a learning method in which generalization of the training data is, in theory, delayed until a query is made to the system, as opposed to eager learning, where the system tries to generalize the training data before receiving queries.
So this means that actually in KNN we don't make any pre-training. As the new data arrives, we iterate through our current examples and decide new data's class. So until the query, which means the new data arrives, we don't make any training. That is why it is lazy learning. That is why the learning stage is instant uh, in KNN, because there is no learning stage actually. However, testing stage is pretty exhaustive, because whenever a new data arrives, a test data arrives, it has to check the let's say close pairs or all of the pairs, depending on the KNN model we are using. We have seen them in the previous lecture. So the positive sides of KNN.
KNN-Pros. The training phase of K-nearest neighbor classification is much faster compared to other classification algorithms. There is no need to train a model for generalization. That is why KNN is known as the simple and instance-based learning algorithm. KNN can be useful in case of nonlinear data.
So this is important. It can be useful in nonlinear data, a data that cannot be linearly separable. can you separate this data linearly? What does linearly mean? Linearly means that with a single line. Can you separate it? Wherever you draw a line, you can't separate this data linearly. Your line has to be like, let me show you. I am going to take a picture of this to make some drawings. Okay. So, okay, a line is something like this. Can you separate this data with a single line? Wherever I put my line, it is impossible to separate blues and reds. However, without linear lines, with a line like this, let me show you a line like this. I can separate reds and blues, as you can see. So KNN can work very well for this kind of data distribution. Okay.
It can be used with the regression problem.
So what is regression problem, if you wonder?
A regression problem is when the output variable is a real or continuous value, such as salary or weight. Many different models can be used. The simplest is the linear regression. It tries to fit data with the best hyperplane which goes through the points.
Okay. So now you have the idea about regression problem.
Output value for the object is computed by the average of k closest neighbors value.
Okay, this is the default model of KNN. And negative sides of KNN.
KNN-Cons. The testing phase of k-nearest neighbor classification is slower and costlier in terms of time and memory.
Testing, because each time a new data arrives, it has to check the nearest neighbors based on the k value.
It requires large memory for storing the entire training data set for prediction.
So you see, this is also important.
KNN requires scaling of data because KNN uses the Euclidean distance between two data points to find nearest neighbors.
So your data has to be scalable. So if you are wondering scaling of data, we have seen that in the previous lecture as well.
Scaling. This means that you're transforming your data so that it fits within a specific scale, like 0 to 100 or 0 to 1. You want to scale data when you're using methods based on measures of how far apart data points, like support vector machines, or SVM or k-nearest neighbors, or KNN.
So support vector machines and SVM means the same thing, or KNN and K nearest neighbors, same thing. We usually scale the data between the 0 and 1, usually based on the algorithm. So your data should be scalable.
Euclidean distance is sensitive to magnitudes. The features with high magnitudes will weight more than features with low magnitudes. KNN also not suitable for large dimensional data.
For example, text classification. In text classification, every word is usually a dimension, a feature. Therefore, you can have hundreds of thousands of dimensions if you consider each word as a feature, as a dimension. Okay. So KNN is only useful for certain data, as for many of the other models. Same.
Decision tree model.
In decision tree model, we expect data to be categorical.
Axis-aligned splits, cuts of the data.
So the bias of the decision tree,
Bias.
or generally,
The bias of a model is how strong the model assumptions are. Low bias classifiers make minimal assumptions about the data. KNN and DT are generally considered low bias. High bias classifiers make strong assumptions about the data.
Okay, so then we start to see linear models.
Linear models.
The strong high bias assumption of linear models is,
A strong high bias assumption is linear separability.
so what is linear separability? Means that you can separate data with a linear line like this. So this first example is linearly separable, however this one is not, obviously.
In 2 dimensions, can separate classes by a line. In higher dimensions, need hyperplanes. A linear model is a model that assumes the data is linearly separable.
So if you have only 2 features, which means you have 2 dimensions, you can separate classes by a line. You can. You may not be able to as well. However, if you have more than 2 features, which means you have more than 2 dimensions, you will need hyperplanes. We will see them. So this is a model that can be linearly separable. As you can see, it has 2 features. That means it is 2 dimensions, and you can separate it like this. And hyperplanes.
Hyperplanes. A hyperplane is plane in a high-dimensional space. What defines a line? What defines a hyperplane?
So this is a bit harder to understand at the beginning. What are hyperplanes? I will try to find a good example of hyperplane. There is mathematical description, but I will try to find some visual explanation. Planes and hyperplanes. As you can see, both of them are academic articles. Let's try to find an image. Okay, this one looks like a good one. Okay, so this is like an hyperplane which is used for every dimension itself. It is still hard to understand, but you will understand by the time. Okay, let's continue.
Defining a line. Any pair of values W1, W2 defines a line through the origin.
So any pair of values W1 and W2 defines a line through the origin, and this is the function.
0 equals W1F1 plus W2F2.
So if this is the function and if this is the weights, how would be the lines? Okay, so if W1 is 1 and W2 is 2, for minus 2, what would be the value of F2? It would be 1. Okay, so minus 1 for F1, what would be the value of F2? It would be 0.5, because this is the formula. Okay, So based on the origin, this would be the line of 1 and 2. When the W1 is 1 and the W2 is 2, this would be the line that it generates through the origin. Why? You see, when the F1 is 1, F2 is minus 0.5. You see, like here, let me show it with drawing. So when F1 is 1, it would be 1 here. So we need minus 1 here, and since the W2 is 2, this has to be minus 0.5. Okay, so F1 is 1. So here the F2 is this one. Okay, so let me draw it again with clear lines. Okay, when this is 1, this is here. Okay, so this is being F1 and this is being F2. Based on W1 is being 1 and W2 is being 2. Okay, so this is a line through origin. This is how we define a line. And
We can also view it as the line perpendicular to the weight vector.
okay, so this topic is important.
Classifying with a line. Mathematically, how can we classify points based on a line?
So each point actually a feature of our data. Okay, you see they are scaled between 1 and minus 1 at the moment. So these each of them is a data point feature value of our data. Our data can be anything. They can be let's say blue blue rocks and red rocks, or uh, anything else, and these can be the values of features. What could be the features of blue rocks and red rocks? I think this would be a harder example. Let's think something else. Let's say you have two different uh, I'm thinking a good example at the moment. Okay, let's say you have blue and red cars. Okay, cars. However, red cars are uh, regular taxis and blue cars are, let's say, they are trucks. Okay, so the trucks have higher weight and higher motor size or whatever, and we have the values of them. This is just an arbitrary example. So these are the two features, and based on this data, currently we can separate blue and red linearly. You see, like this. Okay, when we set W1 is 1 and W2 is 2, this can separate blue and red correctly. Okay, so this is a classify satisfying line. Okay, you see these are the results.
The sign indicates which side of the line.
So if it is negative, it is the red side of the line currently, and if it is positive, it is the blue side of the line. So blue class and red class, based on the sign, it is either minus or positive. And with these weights, it is satisfying our classification. You see the blue result is 3 and the red dot result is -1.
How do we move the line off of the origin?
How can we move it? We define a, I think it was called as bias, but we will see that. We change the equality from 0 to something else. If we change it to -1, you see that our line is now moved from origin to here. Okay, so if we are equaling the function as -1, it is becoming like this, from this one to this one. So with this way, with this bias, we can move our line through origin. So
Linear models. A linear model in n-dimensional space, i.e. n features, is defined by n+1 weights.
So what is n-dimensional space? Based on our data set, it can be one-dimensional, two-dimensional, 100-dimensional, based on the number of features we have. Okay, so I will give you a real-world data example. Let's say there are websites that provide data sets. I'm waiting them to open. Okay, air traffic passenger data, for example. Let's check it out. It has a CSV data. Let's find some small data set to explain. I think this site was providing easy data sets. Okay, so Iris dataset is the one of the most famous ones.
This is perhaps the best known database to be found in the pattern recognition literature. Fisher's paper is a classic in the field and is referenced frequently to this day. See Duda and Hart, for example. The data set contains 3 classes of 50 instances each, where each class refers to a type of iris plant. One class is linearly separable from the other 2, the latter are not linearly separable from each other.
Okay, so let's download the data of this data set. Okay, this is the description. And okay, so it says the first attribute is sepal length in centimeters. So sepal length, if you wonder what is that, let me show you with an image. I think this is a good one. Let's open the original image. This is how real world data is turned into features. Okay, so this is the sepal length. You see this. For each type of iris plant, they have calculated the different attributes of the plant. So this is the sepal length, and it is the first attribute, and it is recorded as like this. You see, currently it is in centimeters, so this data is not scaled or transformed into a range. As you can see, it is in centimeters. Then the second attribute is sepal width in centimeters. It is this one, you see. And if you wonder what is sepal width, it is this. So this is the width and this is the length. Okay. And then the third attribute is petal length, and the fourth attribute is the petal width. So there are 4 attributes of iris data. As you can see, first attribute, second attribute, third attribute, and the fourth attribute. So how many dimensions this data set has? How many dimensions? What is the n value in here? Okay. So what is the dimension count of this iris dataset? It is 4 because it has 4 different attributes, features, and therefore this is a 4-dimensional data space with having 3 different possible classes. Okay, so the fifth data provided in the dataset is the class of the datas. So in this case, it is being a type of the iris plant. Okay, and it is defined by n+1 weights. So in this case, the iris data would have, let me show you. Okay, this didn't copy paste properly. Maybe we can do that from here. Okay, the iris data, since it is 4-dimensional, okay, we can change it. It would also have an extra W4 and F4, okay, plus B. So it would have fifth weights since it has 4 dimensions. Okay, and some of them would be equal to 0 if we try to separate them with a single line. Okay, actually this would be a plane. You see, this is not a line anymore. In more than 2 dimensions, it becomes a plane. Okay, so in n dimensions, it becomes a hyperplane. This is important. Okay, in n dimensions, it becomes a hyperplane. In 3 dimensions, it becomes a plane. Hyperplane means multiple planes, I believe.
In geometry, a hyperplane is a subspace whose dimension is one less than that of its ambient space. If a space is 3-dimensional, then its hyperplanes are the 2-dimensional planes, while if the space is 2-dimensional, its hyperplanes are the 1-dimensional lines. This notion can be used in any general space in which the concept of the dimension of a subspace is defined.
Okay.
In different settings, hyperplanes may have different properties. For instance, a hyperplane of an n-dimensional affine space is a flat subset with dimension n-1, 1, and it separates the space into 2 half-spaces. While a hyperplane of an n-dimensional projective space does not have this property.
Okay. So this is the definition of hyperplane. Technical description.
In geometry, a hyperplane of an n-dimensional space V is a subspace of dimension n-1, or equivalently, of codimension 1 in V. The space V may be a Euclidean space or more generally an affine space, or a vector space or a projective space, and the notion of hyperplane varies correspondingly since the definition of subspace differs in these settings. In all cases, however, any hyperplane can be given in coordinates as the solution of a single, due to the codimension 1, constraint algebraic equation of degree 1.
Okay, these are all mathematical algorithms. They are really hard to understand in a short time. It takes some time. Okay, so let's continue.
Classifying with a linear model. We can classify with a linear model by checking the sign.
Okay, so if the sign is positive, we can classify as positive example, and if the sign is negative, we can classify as negative example. How? In which case, this is in linear model. Okay, with linear model, we can separate only into two classes maximum. So if you are going to use a linear model, your linear model can only classify up to two classes because it uses a linear line.
Learning a linear model. Geometrically, we know what a linear model represents. Given a linear model, i.e. a set of weights and b, we can classify examples.
Can classify examples into one of the classes. It can be positive or negative. Let's say this green one is negative, and this red one is negative, and this blue one is positive, and this red one is negative, and this blue one is positive, this yellow one is positive, and this yellow one is negative, and this blue one is positive. So blue is positive, yellow triangles are positive, all others are negative.
How is this learning setup different than the learning we've done before? When might this arise?
Okay, we will continue.
Online learning algorithm.
So there is labeled data and our data.
Only get to see one example at a time.
So with online learning algorithm, only get to see one example at a time. And with that example, it tries to classify it correctly. Okay. So 0, 0, 1, and 1, and other ones. So the current model, what does it say?
What does this model currently say?
So the W1 is 1 and W2 is 0. Okay. So this is the separability of these weights. So this side is positive and this side is negative. Okay. Okay, so
Is our current guess right or wrong?
let's check that whether it is correct or not. 1 multiple product minus 1 is minus 1 plus, so this side is minus 1. 0 product 1 is 0, so this is actually minus. However, this instance is supposed to be positive, so our current weights, these are incorrect. We have to modify these weights so that this positive class can become correctly classified. Currently it is classified as negative because the sum of weights multiplying with the future values is negative. Okay. So you see it is minus 1 because 1 product F1 is minus 1 and 0 product F2 is 0. So that is minus 1.
Predicts negative, wrong. How should we update the model?
We should move to this direction.
Should move this direction.
Okay, this direction we should move. Therefore,
A closer look at why we got it wrong. We'd like this value to be positive since it's a positive value.
okay, so this equation should result in positive, and
Which of these contributed to the mistake?
so our features are minus 1 and 1. So which one contributed to this mistake? The contribution has came from W1 because the first weight was minus 1, I mean the first attribute was -1. Therefore, W1 contributed in the wrong direction.
Contributed in the wrong direction. Could have contributed, positive feature, but didn't. How should we change the weights?
So we change the weights in their contribution. Since this one contributed wrong, we decrease its value, we decrease its contribution. Since this could have contributed positively, we increase it. So this is how we update the weights. Then the weights become 0 and 1. And previously it was 1 and 0. So we decrease it the weight 1 and we increase it the weight 2. Okay. So the weights are changed.
Graphically, this also makes sense.
Okay, so let's recalculate.
Is our current guess right or wrong?
So let's first check this one, whether it's correct or not. With weight 1 is being 0, so this becomes 0. And weight 1 is 1, so this becomes 1. So this is equal to 1. Therefore, this one correctly classifies. Okay. So if these weights can correctly classify this example, let's try it. 1 product 0 is 0, -1 product 1 is -1, and the class of this example is also negative. Therefore, this is also correct. So these weights can correctly classify this example and this example.
Predicts negative, correct. How should we update the model? Already correct, don't change it.
So here we are training a single line classifier, a linear line classifier. We are training it. We are updating its weights, and therefore we are training our model. Weights are used in, let's say, perceptron algorithm. Okay. Different algorithms uses different types of classification. In perceptron algorithm, weights are used. Okay. So any example has arrived, and is our current guess is right or wrong? We can calculate it. -1 product 0 is 0. -1 product 1 is -1. And the result is negative. Therefore, this classification is incorrect. So we have to update our weights again. Okay.
Predicts negative, wrong. How should we update the model?
So in this case, weight 2 has contributed in incorrect way. So we have to decrease it. And weight 1 could have contributed in better way. And however, since this is also negative, we have to also change it. So we move to this direction again, and we update the weights again.
Which of these contributed to the mistake?
So this didn't contribute.
Didn't contribute, but could have. Contributed in the wrong direction. How should we change the weights?
So we decrease the one that didn't contribute, because when we decrease this one, this will contribute in the positive way. Okay, and this contributed in the negative way, so we decrease it again. Okay, when we decrease this contributes in the positive way, and then we decrease this doesn't contribute in the negative way, in the wrong direction. Okay. So the new weights become -1 and 0, and these are all our labels, and we are checking that whether they are correct or not. So -1 and -1 is positive. Is this correct? This one, yes. -1 and 1 is positive. Is this correct? Let's check it. Yes, and these are negative. So we have trained our model to correctly classify each of the examples. I will show here with more details. So this one is -1 and 1. When we calculate it with these labels, I'm going to make bigger, plus -1 or plus equal to 1. So this is correct. Okay. And this one is -1 product -1 plus -1 product 0. This one is equal to 1. This is also correct. And this one is 1 product -1 plus 1 product 0, which is equal to -1. This is also correct. And this one is 1 product -1 plus -1 product 0 -1. So you see, each one is correct at the moment. So we have trained our model to linearly separate two classes. In this example, it is positive class and negative class. Okay. So our training is ended, and our algorithm has converged. Okay. So we are starting to see perceptron learning algorithm, which is one of the most strongest algorithms in machine learning. We are starting with the fundamental, with the core of the algorithm. So try to understand every part.
Perceptron Learning Algorithm. Repeat until convergence, or for some hash of iterations.
So what is convergence, if you wonder?
When formulating a problem in deep learning, we need to come up with a loss function, which uses model weights as parameters. Backpropagation starts at an arbitrary point on the error manifold defined by the loss function, and with every iteration intends to move closer to a point that minimizes error value by updating the weights. Essentially, for every possible set of weights the model can have, there is an associated loss for a given loss function, with our goal being to find the minimum point on this manifold.
So the convergence is
Essentially meaning, a model converges when its loss actually moves towards a minima, local or global, with a decreasing trend. It's quite rare to actually come across a strictly converging model, but convergence is commonly used in a similar manner as convexity is. Strictly speaking, rarely exists practically, but is spoken in a manner telling us how close the model is to the ideal scenario for convexity, or in this case convergence.
So in this case, our loss or our error rate is 0. Therefore, we have converged. Okay. So let's start from beginning again.
Repeat until convergence, or for some hash of iterations. For each training example, F1, F2, Fn, label. Check if it's correct based on the current model.
Okay, the reading is not reading. 1 second, I will pause. Okay, I had a internet outage.
If not correct, update all the weights. If label positive and feature positive. Increase weight equals predict more positive. If label positive and feature negative. Decrease weight equals predict more positive. If label negative and feature positive. Decrease weight equals predict more negative. If label negative and negative weight. Increase weight equals predict more negative.
Okay, so for example, here we have decreased both of them. Why? Because the feature, I mean the label was negative and it didn't contribute. So it is which case here? Uh, it is the case here. Okay. So this case, label was negative, feature was positive because it could have contributed more. Therefore, we have decreased it. Okay, so this is the simplified explanation of perceptron learning algorithm.
A trick. Let positive label equals 1 and negative label equals -1. If label positive and feature positive. Increase weight equals predict more positive.
Okay, I'm not going to read all of them. So here an example is given. So you see increase in first case, decrease in second case, and decrease in third case, and increase in fourth case. Why? Because label is positive and the second label is negative, and I mean positive label is positive 1 and the negative label is negative 1. In that case, you can directly apply the rules here. You can also match them, the cases here, as I just did. So repeat until convergence or for some iterations. Okay, so in our example, how many iteration we did until the convergence? And let's check it out. So we did one here, and I think we did only one for each time. So with 4 iteration, it was converged. We can also set a manual number of iterations. Let's say we can say do maximum 3 iterations. If it is converged, it is converged or not. Use the best case. Okay, so this is important.
How do we check if it's correct?
We check with the prediction product label if it is below 0 or not.
Would this work for non-binary features, i.e. real-valued?
Can this work for real valued data? Yes, of course, it can work for real valued data currently because we just multiply the weights and feature weight, feature value. So they can. This is important. Keep track of weights.
Keep track of W1, W2 as they change. Redraw the line after each step.
So this is a simple practice for you if you want to do that. So this is the beginning. Okay, and beginning weights are 1 and 0. It can be randomly given. and we will try to make it converge or run it until certain number of iterations. However, this can be converged because a line, something like this, would separate all cases correctly. Okay. So currently we are starting with the first case, 0 and -1. Let's calculate it. This is 0 and this is -1, so this is incorrect. Okay. This should be positive. Therefore, we update weights. Okay. So the updated weights are being -1 and 0. Why is that? Because the first value didn't contribute, but it could have been contributed. Okay, because it didn't contribute because the weight was 0, but it could have been contributed as positive. The second value, the F2, has contributed in the negative way, so we increase the value of weight 2 and decrease the value of weight 1. Because if you check the definite rule here, you will see that. Okay. Therefore, the weights become 0 because this has been decreased and this has been increased. So, oh, this is also decreased. Why is that? Let's check it. Ah, this is also increased. Yes, from -1 to 0. So we have predicted correctly. Now we are checking the second case. In this case, 0.5 product -1 is minus 0.5 and 0 product -1 is 0. So this one, the first weight, contributed negatively in correct way, and the second weight could have contributed positively, but it didn't. So we increased this one. Okay. Since the F2 is negative, we decrease this one because it could have been contributed positive, and the label is negative. Therefore, we decrease this one. Let me show you. Label is negative and feature could have contributed positive, so we decrease the weight. Okay, this case, you can see. Therefore, we decrease this weight and we increase this weight, and they become like this. So this is increased by 0.5 and this is decreased by 1. Okay, we used the values here. So let's check it again if it is correctly classified. This product, this is minus 0.25, and this product, this is +1. So this is now plus. This is, let's check this one again since we have updated weights. -1 product minus 0.5 is plus 0.5, and 1 product -1 is -1. Okay, so this is still incorrect. Therefore, we would need to update again. So updating weights has broken this one. However, now these two are correctly classified, so we need to update again. And we update weights again according to this. So new values are like this, and this time this one is incorrectly classified. As you can see, this is the positive side, this is the negative side. So we update weights again, and the weights are like -1 and -1. So this is on the line. Okay, so we update the weights again, and now this one is incorrect. We update the weights again, and now finally everything is correctly classified, therefore it is converged. Okay, and here we can finish the weights. You can do this step by step at home to understand. It is so easy. You just follow the steps here. If label is, let's say, negative and the future contribution is negative, apply the rule here. If the label is positive and the future contribution is positive, apply the rule here. And if the label is negative and the future contribution is positive, apply the rule here. And if label is negative and the future contribution is, the weight contribution is negative, apply the rules here. It is easy. Okay, now so you get the idea of updating weights for only two-dimensional feature space. Okay, so with two-dimensional feature space with a single line, we can separate them. So in this case, which line will it find? It can find many lines that will separate or that will satisfy this classification like this. However, which one is best?
Only guaranteed to find some line that separates the data. Convergence. Why do we also have the some hash iterations check? If we ran the algorithm on this, it would never converge.
Why? Because we can't find a single line that will separate this data. Okay, we can't find a single line. Whatever you draw, it will not separate both classes correctly. Therefore, it will never converge. What would be the best line? The best would be like something like this. Okay, so this would be a classification error, and however, after certain number of iterations, we would stop the algorithm. So that is why number of iterations is necessary. Okay.
Ordering.
For each training example, we will update the data. However, how we will pick the data update? Okay. For example, here we have started from number 4. What if we start from number 3, or what if we start from number 1? It is up to us to start which data to update weights. So the order matters. As you can see, the order matters.
What would be a good, bad order?
So in this case, which one would be good? I think starting from this one would be good because it is incorrectly classified.
Order matters, a bad order.
Okay. So this one is incorrectly classified. Therefore, if we start from updating this one, should break this one. So what is the solution? We continue updating, and we can use,
Randomize order or training examples.
we can randomize it. And what will happen when we examine this example?
What will happen when we examine this example?
This one is impossible to separate. Therefore, we have to stop the algorithm after certain number of iterations.
Does this make sense? What if we had previously gone through all of the other examples correctly? maybe just move it slightly in the direction of correction.
Okay, to solve this problem,
Voted Perceptron Learning. Training. Every time a mistake is made on an example, store the weights, i.e. before changing for current example. Store the number of examples that set of weights got correct. Classify. Calculate the prediction from all saved weights. Multiply each prediction by the number it got correct, i.e. a weighted vote, and take the sum over all predictions. Said another way, pick whichever prediction has the most votes.
okay, so this is water perceptron. In the regular perceptron, we didn't save any of the weights, or we didn't care about which data makes the most significant effect. In water perceptron learning, we check each data and their contribution or change after we update weights, and we vote. Okay, so vote 3, vote 1. You see the weight changes, vote 5 and vote 1. So based on the weight update, whichever has the most vote, it is the best one to pick. So the prediction 8 negative and 2 positive. So voted perceptron learning. I will find a better example right now. Let's find a better example than our slide. I am trying to find a simple example. There are many articles, academic articles, because this is one of the most used algorithms in machine learning. Okay, this is the perceptron algorithm. We have already seen it. I am trying to find a good example for voted perceptron. Generally, it is very hard to understand these algorithms until you find a good example. And finding good examples of these algorithms are extremely hard, because I had also this problem. Maybe you can find some pseudocode. I will pause video for a while to find a good example, so you won't waste. Okay, so I have looked for a good example to explain what is perceptron. However, there weren't any good example for that. But I have found another good lecture related to perceptron. I have uploaded it to our GitHub repository, and now I am going to make some comments based on that. So perceptron is linear classifier. However, there can be multiple perceptrons to classify. We will see that in the future. So there can be 2 dimension, or it can be more than 2 dimensions as well. If there are more than 2 dimensions, we call the linear classifier that separates the data space into the half as hyperplane. Okay, so let's make this read.
In n dimensions, a linear classifier represents a hyperplane that separates the space into 2 half spaces.
So with the perceptron algorithm, we are having a weight for each of the features, okay, and we train every example for a certain amount of iterations or until it converges. Okay, so let's recap from this slide as well. So we have training examples which are element of real space. They are named as x1, x2, x3, and they have a class output. Okay. In this case, they are, since this is a linear separation, there is negative class and positive class, and the negative class is -1 and the positive class is 1. So we initialize all of the weights as 0 in the beginning. How many weights we are having? We are having weights equal to the number of features, dimensions. So you see here, weight 1, weight 2, based on the number of features. So x's are the features, and I said I think x's are the examples. No, x is the feature, and the I is the output class. So we start with setting all the weights as 0. Then we start to calculate output of each training example, and then update the weights based on the prediction. Okay, so here it is starting to explain. If we make a mistake on positive, we increase the weight based on with R. R is the learning factor. Okay, for example, in this example, the R was used as the values of the features. So you see, so the R may change according to your peak. I mean, the how much you will increase or decrease the weight, and mistake on negative will be subtracted. Okay. So you see, it is explained here.
R is the learning rate, a small positive number less than 1.
Okay, then uh,
Update only on error. A mistake-driven algorithm.
okay, then we continue.
This is the simplest version. We will see more robust versions at the end.
Okay.
Mistake can be written as YWT to 11 is less than or equal to 0.
Okay, so mistake on positive is summed and mistake on negative is subtracted. We saw that in our example already, so we know that. And VT plus 1 means that the new weight and it is added to our product XI. Okay. And there is the geometry. We already saw this, and you can also check this at the home yourself. It is on our GitHub repository. So there is some learnability issues to Perceptron if it is a single Perceptron.
Perceptron Learnability. Obviously, Perceptron cannot learn what it cannot represent. Only linearly separable functions. Minsky and Papert, 1969, wrote an influential book demonstrating Perceptron's representational limitations. Parity functions can't be learned XOR. But we already know that XOR is not linearly separable. Feature transformation trick.
Okay, so I am skipping this part. It is all about some mathematical proofing. Actually, you don't even need to or has to, let's say, understand how it works until you need to improve the algorithm. Okay, you can use the already existing frameworks. However, of course, understanding can let you to improve your feature set, data set, make tunings. So it is important, but it is you don't have to use it. Okay. Okay, so now I will try to explain the voted perceptron at my best. However, you may need to try at your home to understand it better. You may need to practice, you may need to write data. So there are 1 to t epoch. What does epoch mean? Epoch means that a single iteration of training of all training examples. Okay, so you see this is a for each loop. First we shuffle the data, our training data set, then for each training example we update the weights. Okay, so this means that v over t means that the new weight, xi means the each feature, so it is updated as weight becomes weight plus r product I product xe. Is the uh, class output, okay, classification output. Then it returns finally the updated weights. Okay, it may return the weights when it's converged or when it reaches the number of maximum epoch. So this is the standard algorithm. Then we can improve the algorithm. So with the standard algorithm, which hyperplane is better? It may stop when it found the H2, or it may stop when it found the H1. So which hyperplane is better? Obviously, the better hyperplane is H1. Okay. However, our algorithm may stop at H2 as well because we just looking for a convergence. We are not looking for the best margin or generalization. Therefore, which perceptron algorithm is you are using makes a difference. You see, margin perceptron, which hyperplane is better? Of course, the better one is H1 because it may classify further data with lesser error because it is more generalized. You see.
The farther from the data points, the less chance to make wrong prediction.
Okay, let's read the description here.
Margin perceptron.
So perceptron makes updates only when the prediction is incorrect. What if the prediction is close to being incorrect? That is, pick a positive and update. When can generalize better but need to choose. Why is this a good idea? Okay. Intentionally set a large margin. And what if the data is not linearly separable? Which one we pick? It is a NP-hard problem. NP-hard is meaning that I think no non-polynomial hardness or non-deterministic. Okay.
In computational complexity theory, NP hardness, non-deterministic polynomial time hardness, is the defining property of a class of problems that are informally at least as hard as the hardest problems in NP. A simple example of an NP hard problem is the subset sum problem.
Okay, this is more about let's say computational complexity theory. So I'm going to pass it. So we come to the voted perceptron. This is better than the regular algorithm to obtain a better hyperplane to separate classes. So the difference in this one is we again have the weights equal to the number of features. However, whenever we update weight, we keep the previous unupdated weights. Okay, so what I mean is, let's say in the first epoch, in the first iteration, I have VW, V2, V3, V4. Let's say, for example, I have 5 training examples. In the first iteration, my weights are like this. Let's say 1, 1, 2, 1. Okay. I'm just giving arbitrary numbers. And this has classified the first training example correctly. Okay, I will do this as correct. Therefore, these weights, since this is the first iteration, I will mention it as k equal to 1. So, VK1 gets plus 1. Okay, because the first example was correct. And then second example was correct, let's say. So VK1 gets plus 1 again. So it becomes, let's say, 2. I will make it like this, 1. And the third example is incorrect. What happens? Then we update the weights, okay, like this. This time it becomes this. So we say the VK1 equals to like this. And the voting of VK1 becomes as 2. So these weights gets voting as 2 because these weights has correctly predicted 2 examples consecutively. Then it's continue checking the examples with the new updated weights, and this one gets, of course, as 1. We name this as, okay, so this is not the iteration count. This is a number. Arbitrarily, this is an index we give to hold previous weights. Okay, so the voting of VK1 becomes 2 and VK2 becomes 1. As you can see here, you see then it increases the k value or m value. Let's make it m, and I'm going to name it as m, so it will be more matching to the slide. Okay. Before, when the third example is incorrect, I do like this. First, I assign may1 as the existing value as. Okay, then I set, actually I had set it, so I increase may value as 1. Then I set, I will tell this as, I will name this as voting. Voting, and I will make this as weights, so it will have a better naming. And then I increase the m by 1, and mv2 voting becomes 1, and mv2 is updating weights. It is becoming, let's say this time, this. Okay, so I continue with the fourth example. Let's say the fourth example is also incorrect. Then I update the weights of mv2. I think we don't need this anymore because it was updated here, and it was also same as here. And here, since it is incorrect, m2 weights were updated here, and it didn't get any voting. Therefore, I am increasing the m by 1. Then m3 voting gets 1. Update weights, and m3 weights become like this, for example. So once the iteration ends, it starts another iteration again, and based on this, every weight gets a voting. Okay, and at the finally, when the training has ended, we use this cm values as a voting weight. Okay, so you see they are the weights are produced, multiplied with the ci value. Okay, so this is vote to perceptron. Based on those votings and summarization, the final output is decided. You know, in linear classification, how we were calculating the prediction? We were calculating the prediction by summing the weight product future value plus bias. Okay, so in the average perceptron, I mean the voted perceptron, there is also another value, which is the vote count of that product, of that weight, and at the finally the sum of all weights is deciding the final output. Okay. So you see, this time we are summing all of the weights and it decides the output. What I mean is, let's say if our feature is value is 1, 2, 3, 4. Okay. So when calculating the final product, they will be multiplied with each weights, each registered weights like this, VM1, VM2, VM3, and all of them will be summed to decide the final class. Okay. The difference of averaged perceptron is, instead of keeping weights of every let's say training example for every epoch, every iteration, we keep the average of the weights this time, and therefore we use lesser amount of memory, and this is, I think, more
This is the
generalizable.
simplest version of the averaged perceptron. There are some easy programming tricks to make sure that A is also updated only when there is an error.
Okay. This is extremely popular.
Extremely popular. If you want to use the Perceptron algorithm, use averaging.
Okay, so average it is like this. You see, they get average and voted on any two are positive. Okay. So I will show you an actual example of perceptron algorithm in the next course. Also, I have found a good visual example of perceptron algorithm. For example, here it will first generate a data. This is our data set, and we will fit a perceptron to this one. Okay. So there are two features, which is x and y here. True slope is 2 point and 689, and there is iteration and the error rate. Let's start. This is the global animation speed. Okay, so you see the line is changing with the iterations, and with just 6 iterations, it has found uh, weights that separates the data correctly. Let's generate another data. Let's generate a harder one, perhaps. Okay, let's try this. So you see, this one took 15 iteration. 15 times it has actually checked all of the examples and updated the weights according to the incorrect examples, and then the weights are calculated. So if you wonder what is learned slope, yeah. Okay, it didn't explain here. Learning. I think this is a mathematical term. Slope of the line. Okay, so I think there are videos to explain it. Maybe there is a image as well. Oh, okay. So the slope is the change in I over change in x. Okay. So the change in I is like this, and the change in x is like this. So this is the slope. Okay. And the learned slope, which one is being this? Okay. And the true slope was like this. So it didn't find the true slope. The true slope is probably the slope that has the best margin. And there is convergence proof. These are all mathematical equations. And then changing the margin. Okay, here, generate data. Okay, so let's try with 50 margin. Okay, so now we have a 50-point margin. It took 6 iteration, and let's try with 1 margin. It took 14 iterations. So you see the error is changing with each updated weight. Let's try with 150 points, and with 1% margin it took 29 iteration, and let's make 50% margin. Okay, it took 5 iteration. You see, if the margin between classes are high, it takes lesser, and if the margin is, let's say, 0, then it takes higher number of iterations. Okay, if the data is not linearly separable, okay, so what is the K? Okay, so let's try it. This is not linearly separable. So after certain number of iteration, or the key value, okay, so when it reaches this value, it is stopping, I think. And this is the value that he has given. Let's try with key value 1. So it took 29. I'm going to make the speed more, animation speed, 10 ms. And let's play with it. Okay, so it has found finally the 0.180 with 28 iterations. Let's make the noise like this and make like this. Okay, so you see now it took 78 iterations, and I wonder what will be the final error rate. Okay, so the final error rate is 0.428 27. Then I will try with like this. Okay, you see now it is 156 iteration. So based on the k value, the number of iterations changes. Okay. And there is also water perceptron. With water perceptron, we can set the number of iterations and try with it. Okay, you see, each line is a weight, and as they get more votes, they become more, let's say, uh, thicker color, so they become more thicker. You see, this one has become pretty black. You also see that it takes a lot of time with voted perceptron. Okay, so you see at the end it calculated the total error because it considered all of the weights, and you see each one has different number of votes. So based on votes and with all the weights, it calculates the final class of each data point. Therefore, the error is 0.133. Let's try this with 10 noise on regular perceptron. I wonder what will be the error rate. Okay, so this is a regular perceptron. However, there is no noise. Okay, there is no noise here as well. Okay, there is some noise here, and I'm going to set the key value as 0, 10, and I wonder what will be the error rate. However, we are not using the same dataset, so this dataset may be better separable than the other one. Okay, it found this error rate. Let's generate another one. Like this. In machine learning or in artificial intelligence, there is cherry picking. I have explained it in the previous lecture. So I can generate random datasets and cherry pick the best one and say that my algorithm has shown a significant performance. However, it wouldn't be fair. Therefore, you should always share your dataset so that other people can also test on it. Okay, you can read this page and try to understand better if you want to, and play with the value as there. Okay, so we shown the voted perceptron, and there is also average perceptron. In this case, it just takes average of weights. Okay, so with the voted perceptron learning,
Training. Every time a mistake is made on an example, store the weights, i.e. before changing for current example. Store the number of examples that set of weights got correct.
okay, this is the training phase, and once the training ends,
Classify. Calculate the prediction from all saved weights.
you may have saved thousands of weights for just a low number of data, for example, just for 10 features, and if it has got 100 iterations, it can cause you to have even 1000 weights or more. It depends on your number of iterations and number of features you have.
Multiply each prediction by the number it got correct, i.e. a weighted vote, and take the sum over all predictions. Said another way, pick whichever prediction has the most votes. Can require a lot of storage. Classifying becomes very, very expensive.
So therefore, this is not a preferred method of perceptron algorithm. Then there is average perceptron. In this case, the weights are calculated each time, and then they are divided to number of calculations. So they get the average of their value. Okay, you see these are the number of correctly predictions, and they are summed, and then they are divided.
The final weights are the weighted average of the previous weights.
Therefore, you don't have to keep track of all of the weights. Okay.
Why is it called the Perceptron Learning Algorithm if what it learns is a line? Why not line learning algorithm?
Because it is very similar to our nervous system.
Our nervous system.
In our nervous system, there are dendrites, axon, and synapses. You see, this is a I think dendrite, and it takes a lot of let's say activation. Sorry about noise. Okay, it takes inputs from the synapses, and based on the activation limit, it activates.
Our nervous system, the computer science view. The human brain is a large collection of interconnected neurons. A neuron is a brain cell.
Sorry about this.
Collect, process, and disseminate electrical signals. Neurons are connected via synapses. They fire depending on the conditions of the neighboring neurons.
So there is node A neuron and with W, and there is node B a neuron.
W is the strength of signals sent between A and B. If A fires and W is positive, then A stimulates B. If A fires and W is negative, then A inhibits B. If a node is stimulated enough, then it also fires. How much stimulation is required is determined by its threshold.
So you see each neuron is stimulated by many neurons, and some of those neurons determines that it fires or not, and this is the single neuron perceptron.
A single neuron, perceptron.
So that is why we call it as perceptron. You see there are inputs x1, x2, x3, x4, and each one has weights. Okay, so there is a threshold function, and based on this threshold function and some of the inputs multiplying with weights, it fires or not. Okay, so with perceptron algorithm we can have thousands, hundreds of thousands of perceptrons, and combination of them would determine our output. Okay, based on the activation function.
Possible threshold functions. Hard threshold. If in the sum of weights greater than equals threshold 1, 0 otherwise.
So this is a hard threshold. If it is bigger than 1, it is 1 or it is 0. There's sigmoid activation function.
Sigmoid.
It is like this. You can also use this, and you see if it is the threshold of 1, so 1 product 1 is 1, 1 product minus 1 is minus 1, 0 product 1 is 0, and 1 product 0.5 is 0.5. So when we sum all of them, this is 0.5, and the threshold is 1, therefore it is 0, because the threshold was 1 and the weighted sum was 0.5.
Weighted sum is 0.5, which is not equal or larger than the threshold.
Therefore the output is 0. If we increase this one to 1, then it would fire, or increase this input to 2, it would fire. In this case, it is 1 plus 0 plus 0 plus 0.5, so it is 1.5, then this one fires. Okay. So the weights here are being the axons, probably, or the synapses, I'm not sure. And based on the input, it fires or not.
History of neural networks. McCulloch and Pitts 1943 introduced model of artificial neurons and suggested they could learn. Hebb 1949 simple updating rule for learning. Rosenblatt 1962 the perceptron model. Minsky and Papert 1969 wrote perceptrons. Bryson and Ho 1969, but largely ignored until 1980s, invented back propagation learning for multilayer networks.
So you see the history of neural networks backs to two early times. Okay, usually algorithms are discovered much earlier than today. However, they weren't useful to us only until recently. Until recently, we didn't have the hardware or the data to utilize these algorithms, let's say, efficiently. Okay. So there are 4 videos I want you to watch. Okay, 4 parts of videos. These are extremely important and useful, and you will get the idea of perceptrons. Believe me, I'm not going to play these videos and explain them because they are already explained with subtitles. Even they have uh, Turkish subtitle as well. Okay, and they have English subtitle as well, of course. Oh, I think the subtitles are automatic, not. Oh, it is manual as well. So when you watch 4 videos, you will get the idea of perceptron and what they mean. Okay, so please watch this. And after watching, if you still have
What exactly happens to each weight?
if you still have questions, please ask them to me on our Discord channel, okay, or from email. But please watch all 4 of these videos. This will change. Okay. So they are total 19 minutes, 21 minutes, so 40 minutes, 53 minutes, and 63 minutes. These videos will change your look and understanding how neural networks works, how machine learning is able to achieve some great AI. Neural networks is very strong. They are very popular, uh, and they are likely to be the strongest algorithm of machine learning in today's world. So please watch all these videos and ask me any questions that if you don't understand any part of those videos. I plan to make a practical example of perceptron algorithm in C# code in the next lecture. Until then, please watch our lecture 5 video and watch these 4 videos so you will have the idea of perceptron algorithm before we start coding an example of it. Okay, so I am going to upload the latest slides to our GitHub repository. Okay, I have added links to our GitHub repository for Discord channel. Okay, so if you don't know how to use Discord channel, this video is uploaded to our YouTube. Okay, then there is the Discord link to join in our Discord channel of courses. You can watch this video to understand how to use Discord. Then you can join our lecture channel from here, 5, and you see now there are announcements and messaging part, so you can ask your questions from here, read the announcements and such. Okay, hopefully see you next week. Stay safe.